Hmm? Not on that. This is correct. You just need to unmute on the mic.
Right.
That's the switcher. It's okay. I'm happy to use my laptop.
All good?
Yes.
Let's give it one more minute. Now we know who comes inside from that door. Okay, maybe it's good to get started. Okay, welcome to another Safari EFCL joint seminar. Today we have Professor Boris Grot from University of Edinburgh. Boris and I go a long way, yeah, starting from UT Austin. I remember the first time I met you was when I gave a lecture in Yale's class, and you asked questions about run-ahead execution.
That's right.
And then we worked together at Microsoft Research. He was a part of a brilliant set of people who were together with us, Microsoft, for the summer, if you remember.
Of course.
We had a good hike also. Yeah. Yeah, he did his PhD at UT Austin on interconnects. And then after that, he did a postdoc at EPFL. And then he moved to University of Edinburgh, where he's been doing a lot of interesting work on microarchitecture, prefetching, function as a service, and many interesting things, energy efficient systems. And he was the Micro 2022 program chair. I think he ran a very nice process, in my opinion. that was it's not always nice, as we know, these processes, but that was very nice. And then he also was the general chair of HPCA 2024, which was very nicely in Edinburgh. And he received a bunch of awards, which I'm not going to iterate over here. But today he's going to talk about some of his recent work and some of the open source infrastructures that they have put out into the community, which has been having a lot of interesting and nice impact. Boris, please go ahead.
Thank you very much. That was a really, really kind introduction, Owner, and a nice recap of how long our relationship, how far back it goes. Okay, great. So it's a huge pleasure to be here. Thank you for everybody who is here in person. Thank you for people online for joining. So by way of introduction, so pretty much all of my work, to be honest, is centered around servers, data centers, stuff that runs in the cloud. And I'm a really, really big believer in that context of working across the stack, really understanding what the software is doing in order to optimize systems, be it in software, in hardware, or increasingly across the stack, software and hardware together. And that is really kind of what this talk is about. So it's looking at serverless. I'll tell you what serverless is. But again, this is kind of understanding software and then trying to make hardware a little bit better and more efficient for a particular important server domain. Okay, so I don't expect people to know what serverless is. I'm sure some of you do. And in that case, please excuse kind of potentially a part of the talk that may be a little bit boring for you because it may be a recap. But just to get everybody on the same page, let me explain serverless. So I'll explain it in terms of kind of understanding how we arrived at the serverless model. And then I'll tell you exactly what the serverless model is. So, traditionally, the way we would run complex applications in the cloud would be, by renting a big fat virtual machine and running everything there, right? So I'm showing kind of an example here, right? So imagine we have some sort of an online shop, right? There's some kind of a front end. That's what the customer, the client is interacting with. There's a bunch of services that are essentially kind of like in the back end, right? So maybe what you see in the picture here is a catalog and a recommendation system and some accounting software, right? And then all of this is backed by database. All right. So the problem we have here is, let's suppose that the load on the service increases and that one of the services, only one of them, becomes a bottleneck, right? And so we need to provide more processing capability. And in this kind of a model, the only way we can do that is by basically cloning the virtual machine, right? Spinning up another one or two or however many virtual machines they need in order to accommodate the increasing load on the service, right? And this is not great, right? Like essentially we're replicating things at a very coarse granularity when only one little part is maybe the bottleneck, okay? So this kind of observation gave rise to a better process paradigm called microservices, where the functionalities were decoupled from each other and deployed in the cloud individually, as a collection of virtual machines, essentially like this picture shows, right? And so in this kind of a paradigm, right, if one service becomes problematic, right, we can simply replicate that particular service, right? So we can just spin up a bunch of virtual machines that are only running that one service and not everything else, right? So this is obviously better in terms of scalability, cost efficiency, right? Resiliency, I mean, there's just like a lot of benefits. And so that is normally how complex software is run in the cloud. It's run at the granularity of microservices, right? But this is still not an ideal model, right? This is not an ideal model. So why is it not ideal? Well, these units, these entire services, they're still reasonably fat, right? And any non-trivial service is ultimately composed of a bunch of much smaller functionalities. All of you guys understand code, right? You understand how code is structured, right? And so, there's many, many, many degrees of encapsulation to any non-trivial piece of code, right? And so, while this model is better than the original model, it's still relatively coarse-grained, right? It still has inefficiencies. And then there's another limitation, which is in order to have any piece of the service available and online, we need to have, at least one instance of that service running, right? At least one instance of a virtual machine running. And then if we want to have resiliency, we actually need to have a few instances running, right? And we got to pay for these instances, no matter if we're processing requests or we're not processing requests, okay? And so these observations gave rise to kind of an even finer grained paradigm of deploying and running software in the cloud, and that is the software paradigm, right? And that really takes this idea of disaggregation and modularity to like an extreme, okay? So here's kind of the basics of serverless, right? So, complex data center applications are organized and deployed as a collection of stateless functions. Okay, the functions are invoked on demand. So for example, one function can call another function, or a function can be invoked via some sort of a trigger, like a user submitting creating an HTTP request. Now, functions are stateless, and that turns out to be a key aspect of this execution model, right? But just because the functions are stateless, applications are still stateful, right? It's just that any state that the application needs to manipulate and maintain across requests would be externalized, for example, in some sort of a database or an object store, something like that. Okay, now another really important aspect of the serverless model is that scaling and load balancing is fully 100% managed by the cloud provider. Okay, effectively, all that the developer does is they upload their function or collection of functions as a bunch of containers to the provider, and that is it, right? And then the magic just happens, right? So the provider will scale the function instances based on demand, so that includes scaling up and scaling down, right? And one of the really cool things with this model is that a service can be fully available with 0 instances running. And that is hugely attractive, right? Hugely attractive, because when you have a period of idle time, right, you don't have to pay for anything, right? It's a true pay on demand, run on demand kind of model. Resilience is provided at the same level. Functions are simply spun up based on necessity. Okay, so that is really, really awesome. There's another cool thing here, and that is the fact that developers, unlike for traditional virtual machines where you would pay for all the VMs you have, regardless of the load on the VM, right? In serverless, you only pay when the function is running. Okay, so the binary model is the amount of time that a function actually runs, right? And there's a multiplier for how much memory and how much CPU the function is using. Okay, so it's really truly pay per use, run on demand. Okay, but the interesting side effect of this, is that developers have a real financial incentive to reduce the footprint, memory, and the runtime of their functions, because they're literally paying for that at the millisecond granularity, right? Okay, so it's clear what the developer is getting out of this. Why are the cloud providers interested in this, right? Compared to virtual machines, where it seems like, hey, this is really cool, like customers pay even when Like they're not processing requests. Why are cloud providers interested in serverless? So the reason is that they get extremely high density and utilization at a server level, right? So it's a really great way to deal with things like stranded resources, where maybe you have a server with, I don't know, 32 cores and 31 cores are utilized, and there's just half a gigabyte of memory left. Like maybe there's no good VM you can like, squeeze into that server. Serverless is a great way to utilize these stranded resources by running these very lightweight functions. So it's a win-win. It's a win for developers. It's a win for cloud providers. Okay, so that's the intro for serverless. What are the implications? Very, very high level, right? So the good news is developers love the fact that their programming model is completely unaffected. They really don't have to think about the fact that they're deploying stuff in a serverless manner, right? They're just writing their normal code, kind of thinking about microservices, disaggregating things as much as possible, and then they're just shipping containers to the cloud, okay? And they love the fact that it's pay-per-use. The bad news, though, is performance can be rocky and efficiency can be low, right? The reason for this is that as a developer, you're no longer in control of scale up and scale down, particularly scale up. You're really trusting the provider to scale based on demand. The provider doesn't really have much incentive to enable instances when there's no demand, right? So basically, functions may need to be cold started, so started up in the critical path of requests arriving, right? And so customers may experience that demand. Functions are stateless, so there's a lot of communication with other functions that is, again, exposed. Come in. So communication efficiency is really important, and a lot of research shows that kind of function to function and function to storage communication is a big bottleneck, right? And then there's a high degree of interleaving on servers that are running a lot of serverless instances, and that leads to poor microarchitectural efficiency. All of these topics have become huge bodies of research, particularly the first two. I'll mostly focus on the last one in this talk. But again, like the point here is that there's a ton of research opportunity in the serverless domain, okay? But in order to do research, we need to have access to a stack. We need to be able to run things, to understand what's going on under the hood. And that stuff that we're running needs to be representative, right? And so when we started working in the space several years ago, we kind of came to a realization that while every major cloud provider has a complete, monetizable serverless stack, all of them are proprietary, and it's really difficult to do research. The stuff that was open source was not entirely representative of the state of the art. And so that basically led us to develop kind of like a complete open source software stack for serverless. Essentially, like we developed our own full serverless stack, okay? And of course, we did this by taking state-of-the-art representative industry-grade components and just simply gluing them together, okay? So for cluster scheduling and function kind of deployment and management, we took Kubernetes and Knative, right? Containers, micro VMs. So let me just for a second tell you about micro VMs. So generally speaking, in majority of clouds, serverless functions run in VMs, just like normal software runs in VMs. And then within the VM, you have containers. The reason why everybody wants to run in VMs is purely for security reasons. Nobody wants a VM, but kind of security principles dictate that VMs are the way to go, okay? The problem with traditional VMs is that they're long to boot. They take about a minute, give or take, to boot a VM, right? And so kind of this whole, hey, let's spin up things on demand that serverless model advocates kind of means that spinning up a VM that takes a minute to spin up in the critical path of a request is not a good option. And so what providers did was they came up with incredibly lightweight micro VMs by stripping out tons and tons of stuff, specializing certain components to serverless environments, right? And so that gave rise to, again, proprietary micro VMs like Firecracker and AWS, gvisor for Google, and so forth. But they're open source. So they're proprietary, but they're open source. And so we support both of these in our stack. And then communication fabric, we use gRPC, right? And so we kind of glued it all together, a bunch of glue logic kind of to make it all work. And we call the stack vHive, okay? So in addition to all of these components I already talked about, I should also say that when we kind of built all of this, we were in touch with AWS, and kind of we got a lot of feedback from them, and sort of, at least at the time, we felt that what we have was loosely representative of what AWS had. We also have a bunch of benchmarking and performance analysis tools like OpenTelemetry for distributed tracing, top-down for microarchitectural studies, stuff like that. Okay, so yeah, that's seen a lot of adoption since we released it a few years ago. We also built a benchmarking suite with a few dozen kind of standalone serverless functions that are really great for microarchitectural research. They also run in GM5 full system simulator, and we provided support for running containerized function images, right? But also we have several complex applications like ML stuff, video analytics, distributed compilation, things like that. So these are really sophisticated serverless workflows that allow people to do kind of at-scale studies on complete meaningful applications. Okay, so we call this the vHive ecosystem. I'm not going to spend too much more time talking about this. Everything is online. Everything I'm talking about today is open source, right? So I already covered the vHive and the benchmarking framework. We have a tool that allows you to do your own a benchmarking of serverless clouds, and we have a dashboard that actually continuously benchmarks performance of a few serverless cloud providers like AWS, Google, and Azure, and so forth. And so it's a cool way to see trends over time. Azure is not great, is what we have found. And then let's see, another tool we recently released, it was actually in collaboration with Anna Klimovich's group here at ETH, allows you to take an industry and a cluster scale trace of serverless executions, strip it down to, like, for example, something that can run on a single machine, map it to real world functions, and we have like a mapper tool, and then generate realistic load on a server, right? So like you're literally running functions with kind of invocation rates and function profiles that are very representative of the real world, right? And so that allows you to do kind of meaningful, for example, microarchitectural benchmarking or kind of control plane or data plane benchmarking with, you know, real code using invocation patterns that are representative. Okay, so that was kind of a bit of a background and a bit of advertising of our tool chain. Like I said, all of this is available. Like if anybody wants to play with this, we're super happy to help you out to bring things up. But kind of now what I want to do is switch gears a bit, and please come in.
Is this for the scavenger hunt thing?
Probably not, no. No, but you're still welcome to come in. Maybe not. Okay, so the question here is, what kind of research can you know, this kind of ecosystem enable? Yes, please. Yeah, questions are great, by the way, so everybody is welcome.
I have a stupid question. So basically, the serverless function needs the whole VM to, like, to boot the whole VM. Am I correct?
So I think you're saying, like, to run a function, you need to boot a whole VM, right? That's the question?
Yeah.
Okay, just want to make sure I understood it. So we have to kind of decouple these things. So a serverless function is an abstraction, right? So it's like a piece of stateless logic that can run. You don't need to run it in a VM. It is not a hard requirement. It just, most cloud providers choose to run them on VM for security reasons. But VMs are, you know, a sandbox, and functions is just code.
So yeah, I get this. So then why vHive uses a micro VM? Like, can you just like implement it on like some lighter way?
Yeah, so the reason why we use micro VMs is because that is what cloud providers use, because they boot super fast, right? So in about 100 milliseconds, you can boot up a micro VM, right? As compared to a full minute. So again, this is not something that we're advocating. We're sort of taking an opposite approach. We're doing what the cloud, like main cloud providers are doing, and we're just replicating them to have an open source stack.
So I'm sorry if I'm interrupting this too
Cool.
long, but like, is there any application in like any like implementation that does this better?
So some people, and I think that there are actual clouds that don't use micro VMs. So for example, there's a popular serverless runtime called OpenWhisk that basically runs bare metal containers, right? That is an option. Most providers don't want to do it for security implications. The VMs are pretty lightweight as it is. It's not zero latency to boot, zero overhead, but it's pretty damn light, but it comes with a bunch of limitations that are way beyond, you know, this talk. It is a research area, right? It is definitely a research area. And in general, like a lot of people think that VMs are not a great abstraction for the cloud, but I think that's a very different topic.
Yeah, I think I got a good enough understanding.
Cool. Okay.
Thank you. Yeah.
No, great. Yeah. Awesome. Okay. So let's see. So in this talk, I'll mostly focus on what happens when a serverless function executes in a server. And this will be a microarchitecture talks, right? So I'm not going to talk about kind of system level issues. And so, yeah, so let's dive in and look at what happens when a serverless function runs on the server. So what's really interesting, and this is kind of the whole like, hey, we need to understand what's going on in software land happens, is there's some really interesting, unique characteristics to serverless functions. So for one thing is they tend to have pretty short execution times where a few milliseconds is actually pretty common for an entire function durations, right? The building granularity for serverless functions is in the order of 1 millisecond. Certainly in AWS, that's the case. And you have to remember that as a developer, right, somebody who is running code using the serverless abstraction, you're paying for the execution time. So you really have a financial incentive to minimize the runtime, right? Now, like we can contrast like something that runs for a few milliseconds with a Linux schedule in Quantum, which is something in the order of 10 to 20 milliseconds, right? This is much, much smaller than a schedule in Quantum. In Linux today, right? Very small memory footprint. So again, using Amazon AWS as a representative example, the smallest serverless function kind of capacity you can buy in terms of memory is 128 megabytes, right? It's tiny, okay? Also, serverless functions tend to have relatively infrequent invocations where a bunch of industry players have provided, like released traces and provided characterizations of their serverless deployments. And what you'll see is that functions are invoked relatively infrequently, kind of at the granularity of seconds, maybe minutes, or even less frequently. This may seem surprising, right? Because if this is such an amazing execution model, why are these things invoked infrequently? The reason has to do with pricing. So per unit time, serverless functions are way more expensive than a VM, like just simply way more expensive, right? So if you have a very large sustained load, right, like your Google search or whatever, you know, like you have a service that is really popular, it's just simply not economical to run it on serverless functions. Like it's just simply not economical, right? Also, the issues that I mentioned, like cold starts and whatever, don't give you the necessary degree of performance predictability that you may get with a lightly loaded virtual machine, right? So pricing dynamics and deployment dynamics also kind of dictate cases where serverless functions are beneficial and where they may be, you know, uneconomical or may not have sufficiently good SLO. Okay, so what are the implications of this? Well, the first, and like this is really, I think, the most exciting one for microarchitects, is that you can put thousands of functions on a single server. Thousands, right? Like if I have a server today with 100 gigabytes of main memory and, you know, many dozens of cores, I can easily support thousands of co-resident functions that are interleaving at extremely fine granularity, right? And so that's kind of like what, you know, this little animation shows, right? If I have a function that is invoked, right, there's going to be a lot of other stuff that runs on that server and probably on the same core before that function is invoked again, okay? And so that is kind of what we're going to dig in pretty much the rest of this talk. So what is the effect of this kind of interleaving? So here in this graph, I'm showing two very, very simple services. One is an authentication service. The other one is an encryption service written in two different runtimes, Python and Node.js, right? The x-axis shows the inter-arrival time of invocations to that particular service, right? So for example, this point would be 100 milliseconds between two requests to the service arriving, Okay, this is running on the server. A lot of other stuff, other functions are running on the same server. And what the y-axis shows is as we increase the inter-arrival time, how does the execution time change relative to baseline, where this particular function, one of these two functions, is executing completely alone, back to back on a single core. So it's like all the microarchitecture is perfectly warmed up, and we're just hammering that particular core one request at a time, right? And as what we can see here is, for inter-arrival times that are typical of what you'll find in the cloud today, right? So it's like 1 second plus. That leads to a higher degree of interleaving, right? So it's like 1 second, for example, between two arrivals to the same request. A lot of other stuff runs on the server, on the core, right? And so what we see is a significant performance degradation. So the function runs for a lot longer than it would otherwise because of the interleaving, right? And essentially the punchline here is that the microarchitectural state of the function gets hammered by the interleaving and the performance degrades. Okay, so I kind of already told you what is happening, but this is a really important kind of big picture to have in mind here. Okay, so we wanted to understand what exactly is happening under the hood. And so we did Intel top-down analysis. I'll tell you in a second what that is on a pretty modern Intel server. So it's an Ice Lake server. You can see the specifications here. We took 20 diverse functions from our function library. Functions are written in the most popular runtimes for serverless. These represent compiled for Go, interpreted and JITted for Python and Node.js runtime. So it's like super different, super diverse kind of functions and runtimes, right? And then we executed back-to-back, and we modeled an interleaved execution. Okay, and so here is the top-level result, which is basically showing the effect on performance when we do back-to-back execution. So again, this is the ideal scenario, right? So functions are executed back-to-back on the same core, so all of the microarchitectural state is warm, and then comparing this to a highly interleaved scenario, right? And so the dashed bars are back-to-back, the solid gray bars are interleaved, and the y-axis is CPI, where remember, cycles per instruction, we want to minimize them, right? So smaller is better, higher is worse, right? And so what we can see here is that under interleaving, CPI increases dramatically, right? By anywhere from like 2 to nearly 3x, right? Kind of across the board. And the reason for that is that under interleaving, the microarchitecture gets hammered. And so when the function is reinvoked, it is experiencing cold microarchitectural state, right? So the caches are cold, kind of like all of the in-core structures are cold, things like that. So then we performed Intel top-down analysis that basically looks at where are the cycles inside the core going, right? Where what we would ideally see is that every single cycle we're retiring some instructions, right? But that doesn't always happen. And so there are kind of three sources of stalls. Stalls are bad. We don't want our cores to stall. So we have stalls due to the fetch, right? Stalls due to bad speculation. So this would be a branch misprediction or a BTB miss, or stalls somewhere in the back end. Could be a structural stall, can be miss for data, for like load, cache miss. And so what we see here is that kind of broadly speaking, front-end bound stalls, which is a combination of fetch stalls and speculation-related stalls, are by far the biggest stall category, and it's the category that increases the most going from back-to-back to interleaved executions. Okay, so the increases by like over 200%, going from back-to-back to interleaved. Now, we did this study original in Ice Lake, then we looked at an older server, we looked at a newer server, so that's Sapphire Rapids, and we saw pretty much identical trends. Like the exact numbers are different, the trends are identical, okay? And so kind of the conclusion here is that the front end is really a key performance bottleneck when functions are warm, they're on the server, right? So the function is not being cold booted, right? So we don't need to bring up the micro VM, right? But a lot of time passes between two invocations of the same function. Okay, and so I'm gonna start by talking kind of the biggest stall category, which is one related to fetch stalls, right? And then, if we're okay on time, I'll talk a little bit about kind of more holistic front-end related stalls. Okay, so kind of looking at this picture, you can see that, fetch stalls go from significant to like absolutely huge. And the question we're asking is, why are fetch related stalls so dominant under interleaved execution? Yeah.
So the question is that the data related stalls, the backend boundness is lower than the front-end stalls, right? So what type of data footprint we are looking at from this?
So the data footprint for these particular functions is really small, right? So these functions don't run for a long time. So intuitively, if a function were to operate on tens of gigabytes of data, it would not finish in a couple of milliseconds, right? So the data working sets are small. Yeah, great question. Yeah, fair.
Is the scheduler, the Linux scheduler, taking into account the reference interval to maybe figure out if your scheduler, not the scheduler, to take into account, for example, that you may have instructions warmer at a specific core for this specific function compared to another
that's
one?
A really, really good question. So basically, like when you're scheduling functions, can you somehow be like, hey, maybe this function recently executed on that particular core, and that would be a really good core to run it at, right? So again, we need to kind of go back and sort of think about what's happening. So the functions, like the time between two invocations of the same function is a second or more on average, right? Generally speaking, more than 1 second. And the function runs for a few milliseconds. So between two invocations, you will have hundreds of other functions that run on a particular core, right? And so the private caches will just be hammered completely. Just forget it, right?
So I guess both then the footprint will be off.
Yeah. Completely destroyed.
Keeping track of what's in would be also very expensive.
Exactly. So you need to keep track of what's in, and also like you may ask like, okay, what if we actually try to pin some cache lines for some functions? Again, that's counterproductive because you would take up capacity, but the invocation interval is so infrequent. Then what is the point? Yeah. Great questions. Thank you.
May I also ask another question? I'm online. Do you hear me?
Yes, please.
Okay, great. So given how many functions are scheduled at the same system at the same time, and also the distance between invocations, would there be cases that we need to bring some stuff from storage system between invocations, or can we just rely on main memory?
Okay, that's also a fantastic question. So in this work, we're assuming that all of the functions that are warm, they're kept in main memory. I didn't want to spend too much time explaining all possible aspects of serverless, but what the cloud providers do is after a function executes, they will keep it what I'm calling warm. That's also what they call it, by essentially keeping it in memory in case another invocation comes along, right? Because the model is that if a function needs to be booted from scratch, the cloud provider pays all the costs, right? They need to load the image from storage, pay for network bandwidth, pay for the cycles of starting up a function. So they kind of want to avoid paying that cost out of their own pocket as much as possible. So they'll keep a pool of functions in memory, and then they'll shut them down after some number of minutes. What you're suggesting implicitly is definitely a legit optimization, because we can keep a hell of a lot more functions semi-warm by keeping them, for example, on a local SSD or something like that. I don't know if providers do that, but there has been quite a bit of work kind of doing that kind of thing in order to boot much, much, much faster than you would otherwise, right? That is a bit orthogonal to what I'm talking about, but it's a perfectly legitimate way to minimize boot time or avoid booting functions.
Thank you very much.
Yep. Okay, right. So we want to understand why fetch-related stalls are so dominant under interleaved execution. At this point, I think maybe kind of based on what I said and some of the questions, you guys already have a good sense for what happens, right? Short answer is data gets evicted from on-chip caches, right? So I'm not even going to talk about L1 and L2 caches because they get thrashed really quickly. Let's just look at an L3 cache. I should also say that the top-down data I showed was for an Ice Lake server. This data is from a Broadwell server. I'm sorry about that. Yeah, we rerun things, but I think some of my graphs are just not updated. It doesn't matter because the bottom line is identical. So the Broadwell server that I'm using for this particular study has 25 megabytes of last level cache. And what you're seeing here, or what you may actually struggle to even see, is that I'm actually showing the miss rate, the MPKI for the L3, the last level cache, for back-to-back executions. And you can barely see little bumps. And that is for data that is not found on the chip. That goes back to Raul's question earlier about the data misses, right? So this would be essentially the data set that is maybe coming in over the network, right? Or, is read from memory or storage or whatever, right, that the function operates on, like a new invocation operates on. We cannot even see any misses for instructions when the function executes back-to-back. Under interleaving, the picture changes dramatically, right? We can see that there's a pretty significant off-chip MPKI, and it's dominated by instruction misses, right? So on average, across all of the functions here, right, the off-chip MPKI for instructions is 18, right? So that means that out of every 1,000 instructions we execute, 18 instructions experience an off-chip miss for instructions. You have to remember that kind of a miss, we're talking about a stall of a couple hundred cycles during which there are no instructions that are entering the core, right? Like that's it. The core is completely exposed to that humongous latency stall. And of course, intuitively, that will completely tank performance, right? So that is basically what's happening here. Okay, so then kind of starting to work toward remedying this problem, we studied instruction traces from consecutive invocations of each functions, and we looked at two things. We looked at the instruction footprint, and we looked at the commonality across invocations for a particular function, right? And so we kind of understood two things. First, and this is probably not terribly surprising, there's pretty high commonality across invocations, right? So over 85% of all instruction cache blocks appear in all of the invocations, like every single one. And then when you look pairwise, that commonality is even higher. And then, for functions that run for just a few milliseconds, right, the instruction footprint is surprisingly high. So it's on the order of hundreds of kilobytes. So basically, functions just stream through hundreds of kilobytes of code, right? And again, the reason why that happens is that a request comes in over the network, so we need to run the network stack in the operating system. Then there is the, the like gRPC fabric, right? There is the actual runtime. Then there's the user code, and that is just to process the request. And then we need to do the opposite in order to send the reply, right? Again, runtime, communication fabric, network stack, and so forth, right? So we're just streaming through tons and tons of code. And so, of course, under a high degree of interleaving, this code will be thrashed, right? This is not a few cache blocks that we can just stash away. Okay, and so kind of thinking about a solution, okay, there's a lot of commonality, and there's a pretty large instruction working set, right? Definitely not something that we can store in an L1I, but it is something that we can, reasonably stash away and bring back. And so that's what we want to do. We want to exploit this commonality in order to record the instruction working set of one invocation and bring it back for the other invocation. Okay, and that gives rise to a very simple instruction prefetcher that we call Jukebox that is really specialized for serverless, and it has a few interesting features. So it's a record and replay prefetcher. So we record the L2 miss stream using a very compact spatial temporal encoding, and we save this metadata directly to main memory. Okay, at replay time, we first read the metadata. And then using the metadata, we prefetch the instruction footprint that was recorded directly into the L2. Now, what is really, really interesting here, and is pretty different from pretty much every other instruction prefetcher that I'm aware of that works on this kind of general record and replay mechanism is that the prefetcher is 100% decoupled from the core, right? So like it just literally dumps the full recorded instruction working set into the L2 without regard for what the core is doing, right? So remember, we're not going for 100% accuracy, right? But we know that the similarity across invocations is extremely high, right? And so this whole idea of let's just dump stuff in order to anticipate as many misses as possible, right? Without necessarily synchronizing with the core, waiting for the core, dealing with, potentially like wrong path execution, stuff like that. This turns out to work extremely well, right? And the other nice thing is that given modern, roughly megabyte-sized L2s, what we find is that the instruction working set fits pretty nicely into the L2. So we're not really thrashing anything by taking this, coarse grain bulk. Let's just dump a bunch of instructions into the L2 approach. Yes, please.
So you're saying that Jukebox is triggered by the function invocation, right? So when exactly do you trigger Jukebox? Like I schedule the function at the core and then I start prefetching? Is it?
Yeah, exactly. So what happens is, so the runtime on a server will schedule a function to run, right? It will allocate resources, and then it kind of looks like a normal process is starting, right? The architectural state is loading. As part of this process, one of the things that gets loaded are memory map registers related to this particular prefetcher that effectively start triggering prefetching, right? So for sure, the function will start executing, and the first few blocks that it encounters will not be any caches because the prefetcher has not run ahead.
So basically, yeah, that's my question. Essentially, like how much are you gaining from the compulsory misses that are in the front of the wave of the function? Because I guess there would be like a slack where your prefetcher is not able to fetch everything quickly and early enough from the memory.
Absolutely. So yeah, the first, I don't know, a couple dozen or something cache lines will definitely miss, right? But again, we're talking about, couple tens. I don't like for that specific thing. I don't have a number for you, cache lines, compared to several hundred kilobytes of state, right?
I have one further question. So when we're talking about the locality across the invocation, so are we meaning that across the invocations of the same function?
Invocations of the same function, exactly.
But do we also expect locality across invocations of different functions? Because if the software stacks are kind of similar, can we expect that their instruction?
That's a really good question. So again, first of all, I think like maybe locality is not the right word. Commonality maybe is a better, better word, right? Yeah, for sure. So this is where things get a little bit trickier. So how much commonality is it across different functions? So that commonality, so now we need to look at like a full container, right? So first of all, there's the container itself, right? And then we have maybe the runtime, Python, Node.js, something like that. And then we actually have the user level code, right? So there's definitely, like the lower parts of the software stack, container, runtime, that kind of thing, that there is commonality. And there have been works in the systems community that have tried to exploit that, right? My understanding is that cloud providers are not particularly keen on those ideas for security purposes, right? Because of security concerns, sorry. But I think like in general, those kinds of ideas definitely have a place and people have explored now. Yeah. I mean, definitely good idea. Okay, yeah, again, I'm not gonna like drag you through like a lot of low-level detail or any low-level detail of this thing. The only other thing I want to mention is that the prefetcher operates on virtual addresses, and that has two really nice side effects. One is that low-level system software is free to move pages around in physical memory, and things continue working correctly. Another nice thing is that the prefetcher has to perform address translation by using the MMU, and that has the really nice side effect of populating the TLB, particularly for instructions. Okay, so that's kind of a nice unintended consequence of this kind of a prefetcher. Okay, cool. I am not going to spend a lot of time on results. I just want to show the top line item here, which is that compared to the baseline for these kind of warm executions of functions that are resident on the server, but they're suffering from microarchitectural thrashing because of other invocations. We're gaining about 18% in performance in full system simulation in Gem 5. Okay, so that's sort of the bottom line. We're covering majority of off-chip instruction misses. So again, kind of like 85% plus. The amount of in-memory metadata that we require is 32 kilobytes. So compared to, like dozens or hundreds of megabytes of main memory that a function is using, I mean, this is really truly nothing, right? And what's really nice here is the metadata is part of the VM image. So when a function gets shut down, the metadata just disappears. There's really no additional cleanup that you have to do on the server. Cool. So before I move on, any questions? Okay, great. I think we're actually doing really, really well on time. So, so Jukebox looked at just the fetch problem. And if you really think about it, it made a pretty good crack at it. It's eliminating the majority of off-chip misses, but it's eliminating them by prefetching into the L2, whereas we're still potentially exposing the core to at least a small latency of accessing of misses in the L1I, right? And then there's the additional problem of misspeculations because we have a called BTB and a called branch predictor. Okay, so in this last part of the talk, I really want to kind of revisit this whole called microarchitectural state problem and ask a question: can we do something for the entire front end holistically? Okay, I will say that this will be a little bit like lower level and a little more microarchitecturally intense. I will do my best to make this as accessible as possible, but please ask questions. Or if you get really bored, feel free to do email. Okay, so let's see. Let's kind of revisit some prior art in front-end mitigation, right? So how do we make sure that our front end is warm and is able to, have the instructions ideally in the L1 and, have warm branch predictor, BTB, and so forth. So we looked at three kind of design points here. The first one is Jukebox, which of course I already covered just now, right? So that is prefetching things directly into the L2, right? And then the second point we kind of need to discuss here, this is relatively state-of-the-art design called Boomerang that is trying to solve two problems. The first problem it's trying to solve is prefetching into the L1I, into the instruction cache, right? And the second problem is prefetching into the BTB. And what Boomerang is doing is it's trying to do this with a single, very lightweight design by exploiting an old idea called fetch-directed prefetching. And the idea here is, hey, we have a branch predictor. Branch predictor can predict control flow. That's what branch predictor is for. Why can't the branch predictor run a little bit ahead of the core front end, right? And so predict a little bit further into the future, right? And so by generating these predictions, right, branch taken, branch not taken, and extrapolating between that, right, we can basically reconstruct the full control flow, sequential, and then jumps, and use that kind of predicted control flow in order to trigger prefetching into the instruction cache. Okay, so that was the idea of back from the 90s called fetch-directed prefetching. And then what Boomerang does is it says, hey, I have a prefetcher. It's prefetching instruction cache blocks. Every instruction cache block will probably have some branch instructions. Branch instructions encode targets. The targets are part of the branch instruction specification, right? Why can't we simply have a small number of dedicated decoders or pre-decoders that will crack cache blocks as they come into the cache, extract branches from them, extract the targets from the branches, and insert them into the BTB. So effectively, I have a BTB prefetcher completely for free as long as I have this thing called FDIP, which pretty much all CPUs have been building for, at least 10, 15 years at this point, all right? So that was the idea of Boomerang, right? So L1I prefetching by virtue of FDIP, and then BTB pre-filling by pre-decoding incoming instruction cache blocks, extracting branch metadata, and sticking it into the BTB. Okay, so this is a really powerful idea here, right? And then we have the ideal completely warm front end where we have perfect L1I, perfect BTB, they never miss. And then we don't have a perfect branch predictor, right? Because that is probably not realistic, but we have a pre-trained state-of-the-art branch predictor, right? So it saw a bunch of invocations, it trained up, and we're gonna maintain its state. So here is our baseline. It's a crappy one. It's just the next line prefetcher for instructions. And then we have the ideal front end, which is, again, ideal L1I, ideal BTB, and then a pre-trained state-of-the-art branch predictor. And we see it's about a 60% performance gap, right? So it's a lot of opportunity there. Okay, we see Jukebox, we saw before, gets us about 18% of this performance. Okay, and then what's interesting is when we don't even look at Boomerang alone, we combine Boomerang with Jukebox, JB's Jukebox, right? We combine them. We're not getting much. This is interesting, right? Because I would expect this combination to be really good because Jukebox is prefetching into the L2. So all the instructions are very close to the L1I. And then Boomerang is supposed to run ahead, get things from the L1 from the L2, bring them to the L1I, populate the BTB. But we see that Boomerang is buying us very little on top of Jukebox, right? So why is that? The answer is that Boomerang and FDIP fundamentally rely on having a warm front end. They require the branch predictor to be pretty accurate in order to anticipate control flow. The problem is that that is not the case, right? The microarchitecture is cold, the branch predictor is cold, right? So it cannot correctly identify branches, right? It cannot correctly predict them, right? And so the end result is that it gets us very little on top of Jukebox, right? So the combined MPKI for the BTB and the conditional branch predictor is over 30, right? So very, very high misprediction rate for speculative, on speculation side. So why is the warm BPU so important? Again, I don't want to spend too much time on microarchitecture, but please, interrupt, ask questions. Again, wrong path execution means that we're prefetching, but we're often prefetching things in the wrong path. And prefetching into the BTB is also ineffective because we're often fetching from the wrong path. And so we're putting things into the BTB that actually should not even be in the BTB because they're on the wrong path. So the cold branch prediction unit, BTB and the conditional branch predictor, is really what's hurting the performance of this whole kind of thread of ideas here. And what we really want to have is we want to have instructions on chip, we want to have a warm BTB, and we want to have a warm branch predictor. And the question is, given that we're solving a pretty narrow problem, right? I mean, come on, it's serverless, right? It's common, lots of people are using it, it's really hot in the cloud, but it's a fraction of the entire serverless server market, and the server market is also a fraction of the CPU market, right? So nobody's going to do crazy things just for serverless. So can we do this in an extremely lightweight design that this could actually be somehow practical and attractive, right? So that's the interesting question here. And so in order to do that, in order to enable this extremely lightweight practical design, we're going to leverage 3 observations. First, control flow repeats across invocations. We already talked about that in the context of Jukebox. Secondly, and this is a new observation, the BTB working set is a complete compressed after a branch is taken, and then until the next taken branch, the instruction flow is consecutive, right? Sequential instructions are executed, right? And then the branches identify discontinuities in the control flow, okay? And then, and so the BTB working set itself can be used as a way to perform prefetching. And then the last observation is that significant fraction of branch mispredictions is compulsory, right? Because the function runs for so little time and it streams through so much code, we don't spend a great deal of time in any particular loop. So there are a lot of cold branch mispredictions. So that is what we really need to target. And so the way we're gonna, and so kind of the key observation is that the BTB working set can be used in order to drive BTB prefetching and instruction prefetching. So this is a cool new observation, but what about the branch predictor, right? So that is the really interesting question we asked. We looked at prior literature, and turns out there's really no literature on warming up a branch predictor, right? So it's kind of like, in a way, the serverless domain is a new domain where this is actually suddenly a problem, because normally the execution time is long enough that the branch predictor will warm up gradually, and then we run for long enough to amortize the warm-up time, right? So a new domain kind of defines new problems. And so our cool new insight here is that a BTB insertion happens only when we have a misprediction, right? So in other words, the very first time a branch is encountered, it's not in the BTB, and it's also, of course, not in the branch predictor. We've never seen that branch. But if a branch is not taken, modern microarchitectures will not insert it into a BTB, because some branches are never taken. So there's no point taking out BTB capacity. So it's only when the branch is taken that it gets inserted into the BTB and the branch prediction is trained. And so we can basically leverage the fact that a BTB insertion corresponds to the first time that a branch is taken as basically a signal saying, hey, a BTB insertion means that branch is taken. Okay, so that is essentially the insight. And so we can turn this insight into a scheme that drives BTB insertions for prefetching and also for branch prediction. So this gives rise to a scheme called Ignite, which is a comprehensive way for restoring a cold microarchitectural front end, right? So what Ignite does is recalls a complete non-redundant control flow graph of an invocation using BTB metadata. And specifically, what it does is every time a BTB insertion happens, it is recorded, right? So we're just recording BTB insertions and nothing else. At replay time, the BTB insertions are used in order to, well, first and foremost, restore the BTB. That's obvious. But also in order to initiate the bimodal branch predictor in the weakly taken direction. Okay, so we initialize the branch predictor and only the stupid bimodal predictor. And of course, we still have the normal conventional high-end H predictor behind it, right? We're just initializing the bimodal predictor here. Okay, and then we can also use the BTB entries in order to drive instruction prefetching by basically inferring discontinuities and then doing sequential prefetching between discontinuities. Okay, so a single set of metadata can drive prefetching into all three structures. Okay, this also integrates with FDIP, which very nicely prefetches into the L1I. Oh, I should add that the kind of BTB-directed prefetching populates the L2, right? And then FDIP will populate the L1I from there. And again, this is fully decoupled from the core, kind of similar to Jukebox, not entirely, but I'm not going to get into the details. Okay, so performance-wise, right, this is what we saw earlier. This is Boomerang combined with Jukebox together. This is ideal, right? And what we see is that the Ignite scheme that I just presented gets more than half of the remaining opportunity, right? It covers over 80% of the BTB misses, over 50% of L1I misses, and what's really, really nice, it eliminates over 60% of all branch mispredictions, right? So again, extremely simple scheme, very lightweight, minimal metadata, but we can use it to drive prefetching into all three structures concurrently. Okay, so was there a question? Oh yeah, okay, please.
There is a question on YouTube. Could Jukebox way of exploiting commonality between function invocations introduce security risk by making timing side channels more exploitable?
That's an interesting question. I don't think we've thought about timing side channels in this context. I guess what I would imagine would be one of the challenges in exploiting timing side channels from an attacker's perspective, I mean, is the fact that we're only prefetching into the private structures. So the L2, L1 and in-core structures. And today, because of the prevalence of timing based exploits, Cloud providers would not schedule 2 virtual machines or micro virtual machines on a same multi-threaded core, right? So I think the fact that we're really mostly targeting private structures would probably help. Yeah, interesting question. Okay, so wrapping up, so let's say I presented kind of vHive stack, or just I very briefly overviewed it, which is a bunch of tools and infrastructure for serverless research. Talked about this problem of invocations kind of being warm on the server, but having cold microarchitecture, so we call this lukewarm invocations. And then I presented 2 schemes for mitigating these, like this cold microarchitectural state phenomenon, right? One is a very simple instruction prefetcher into the L2, and the second one is a comprehensive technique for warming up the entire core front end, and that is the Ignite scheme. I should say that as part of this line of work, that is microarchitectural work, we've also been doing a lot of stuff on the system side for serverless. But in the microarchitectural line of work, we released a bunch of kind of runnable functions that are kind of containerized, and you can just deploy them on real servers, but also in Gem5, the same identical function, and we have infrastructure for running the stuff in Gem5. We also open sourced an implementation of FDIP for Gem5, which is real state of the art, used in modern CPUs that was not part of Gem5 before. So yeah, like we try to open source pretty much everything we do. There have been a lot of people who worked on this. This is definitely not a complete list, mostly focusing on the bits and pieces that I've covered today. We also had some wonderful collaborators work with us on this stuff externally. So yeah, it's been a big effort. With that, I would love to take questions if there are any more. Please.
Thanks, Boris, for the very nice talk. I have a like what potential is left type of question. Basically, you've done a lot of work in this area, and you covered the gap between ideal and current. How much do you think is left, and where are the opportunities, in your opinion?
Okay, that's an awesome question. So what is left? I guess, you know, there are many ways I can interpret this question, because like kind of like what is left in serverless altogether, or warm serverless functions on a server. So I'll give you like a very broad answer. I am not necessarily a believer that any hardware support for serverless, including like this ultra lightweight stuff that I presented, is justified, right? Ultimately, you know, it's a niche, and it's also a pretty rapidly evolving space, right? Time will tell. I think maybe in a decade, if you know serverless continues to grow, this kind of thing will become more attractive. I don't think we're there today. You know, there's still a gap left in what I showed. Does it make sense to do more research to plug that gap even further? Personally, I'm not convinced of that, but some people are trying to do that, right? I do think that serverless presents a lot of opportunities altogether, and there's been a lot of research in the system side of that. But I think that there are nonetheless remaining opportunities in the hardware land, and that maybe has to do with better scheduling of functions, right? And particularly maybe better exploiting some temporal patterns, and really also thinking about the bigger issues like scheduling at system level, right? So like I have a cluster level scheduling. Do I maybe want to prioritize multiple invocations and maybe even multiple instances of the same functions to have them on the same server in order to better exploit temporal locality, both at software and also hardware? I definitely think the opportunities like that left. Yeah. Please.
Oh, so after listening to your talk, I have some feelings that the modern operating system and the microarchitectures design, the goal of them is quite opposite to what serverless functions direct. So I just want to like ask you how much like so to be sure, like can you explore some like non-mainstream CPU architectures, such as the stack machine for like this computers, or anything else that does not lie on the like the compute-centric architecture now?
So I think a stack machine, I think the performance you'd get out of it would probably be so abysmal that it doesn't make sense, right? I haven't tried, but that would be, a reasonable guess. I definitely feel that there is space for lighter weight, more energy efficient, smaller cores for a lot of microservices, and not just serverless, right? And in fact, if you look at the latest generation Intel server chips, their server line bifurcated. And so they still sell servers with fat cores, but they now sell servers it's a line called Sierra Forest with lighter weight, kind of mobile grade cores, whatever that means. I think that makes a hell of a lot of sense. The question is, do cloud providers want to keep increasing the degree of heterogeneity, and is that a big enough market, right? That is a market-driven question, right? But I think the opportunity for kind of more spatial computing, right, where we have a lot more cores, but they're much simpler, I think that's a huge opportunity. But I think it's an economic question, not so much a research question at that point.
Oh, that's too bad for a researcher, but okay, I got the point.
Yeah, exactly.
Okay. No, I was actually thinking on the like a scheduler side, right? So
Yeah.
so is there any opportunity, like so many of these let's say the insights that we had for developing cache replacement or management policies can also be applicable to the scheduler side, that under what circumstances I'm going to co-locate these two invocations of the same functions in the same core, how, like, let's say, creating some sort of microarchitectural signatures to dynamically understand that, okay, this function invocation would likely have similarity with some other function invocation with the history. And then using those information to make an intelligent scheduler that, okay, let's co-locate these two functions on the same core so that they can get some sort of locality or the commonality out of the execution itself. Like, do you see any
So you're saying functions that are not the same, but they're somehow similar, right?
Let's say, yeah. So some sort of let's say signature that the so I'm thinking of, let's say, the scheduler architecture or microarchitecture co-design. So microarchitecture, when it executes a function, it's looking at some sort of signatures, right? And it's feeding back this signature information to the scheduler, saying that, oh, this function has this signature, and the scheduler's job would be to look for common let's say, and cluster the functions based on their signatures, so that when it receives a different invocation of the same function, it would say that, okay, I have executed the previous function with a similar signature in this core, so I'm going to schedule it there. Like, maybe I'm just thinking out loud on top of my head, but does that make sense?
I think, let's see. So I think, like, there's definitely the case that when a particular function scales out, and so there are multiple instances of that function, that is something exploitable. But you would know that, hey, I'm just scaling up, right? Like I'm just creating more instances, right? And so there's definitely a case for maybe trying to co-locate these instances in order to better exploit, temporal locality, things like that. I'm pretty sure that doesn't happen in today's clouds, right? But like, for sure, like, that opportunity is there. But looking beyond, hey, it's just multiple instances of the same exact function, and trying to find exploitable commonality in the cluster level pool of functions, again, I think you're running potentially, I'm guessing a provider would be concerned about maybe some security implications of that, right? And that is probably something that you could do through well-established techniques of kind of deduplication, where you would, for example, right? I mean, this is like established research on the operating system side, trying to find identical memory pages, for example, containing instructions, right, in things like libraries, operating systems, because it's a micro VM, it still has an operating system, right? Things like that, and basically eliminating duplicate pages, right? And so that would be a real effective way to better exploit, temporal locality by having a smaller code footprint, right? And so forth. But also it's essentially independent of functions. You're just simply trying to find commonality across functions, right? So again, I have not heard of providers actually doing that, but there's a lot of work in these kinds of system techniques. Yeah.
That makes sense.
Have quite a provocative, controversial
Oh, great.
question.
Please.
So given that many of these companies who build these software stacks are probably going to shift in the following years into some AI generated code for all these things, like patterns will change towards, do you think patterns will change towards a specific, let's say, AI oriented way of developing the code, which would unlock these commonalities across functions that are not maybe present right now by hand-tuned code, right? And so the question is, like, what based on what Rahul says, like, how much of this AI generated code would we be able to, like, would we co-design, for example, the way the AI would produce these functions and the way we leverage the patterns later? Would it be something that makes sense, or like?
Dude, I mean, you're asking me about like a very hypothetical future, right? I mean, I think that the honest answer is I don't know, and I think I would be speculating, like with such high degree of run ahead here, that it probably would be meaningless. I don't know. I think we would need to see what like AI generated code that actually works on non-trivial problems looks like, and I don't think we've seen that yet. So yeah, that's a good question that we can put on the stack. Thank you.
Okay, thanks everyone for joining, and we're closing the session now. I'll see you again in the defense. Thanks, Boris.
Cool. So I killed Zoom, so that's done. Let me mute the mic.